Now, from the exercises, it appears that we can generalize the previous theorem, but first we need to prove a lemma. So let m sub 1, m sub 2, and m sub 3 be positive integers if the greatest common divisor of all three of the integers is 1, then the greatest common divisor of the product m1 times m2 and m3 is the product of the greatest common divisor of m1 and m3 with the greatest common divisor of m2 and m3. So proof. Let D be the greatest common divisor of the product m1 times m2 and m3. Let D sub 1 be the greatest common divisor of m1 and m3. And let D sub 2 be the greatest common divisor of m2 and m3. Then there exist integers r, s, t, and u such that d sub 1 is equal to m sub 1 times r plus m sub 3 times s, and d sub 2 is equal to m sub 2 times t plus m sub 3 times u. So the product d1 times d2 is the product of the sum m1 times r plus m3 times s times the sum m2 times t plus m3 times u, which is m1 times m2 times r times t plus m2 times m3 times s times t plus m1 times m3 times r times u plus m sub 3 times m sub 3 times s times u. And this is the same as m sub 1 times m sub 2 times r times t plus m sub 3 times the quantity m sub 2 times s times t plus m sub 1 times r times u plus m sub 3 times s times u. Now since D divides the product m1 times m2 and D divides m sub 3, D divides any linear combination of these two integers, and in particular D divides the product d1 times d2. And so d is less than or equal to the product d1 times d2. Now let E be the greatest common divisor of d1 and d2. Then E divides d1 and E divides d2. And since E divides d1, E divides m sub 1 and E divides m sub 3. And since E divides d sub 2, E divides m sub 2, and once again E divides m sub 3. That is, E divides m sub 1, E divides m sub 2, and E divides m sub 3. Now since the greatest common divisor of all three integers m1, m2, and m3 is 1, e must be equal to 1. Now, since d sub 1 divides m sub 1, d sub 1 divides the product m sub 1 times m sub 2. So d sub 1 divides the product m sub 1 times m sub 2, and d sub 1 divides m sub 3. And so d sub 1 divides any linear combination of these two integers. And in particular, d sub 1 divides d. Similarly, since d sub 2 divides m sub 2, d sub 2 divides the product m sub 1 times m sub 2. And so d sub 2 divides the product m sub 1 times m sub 2, and d sub 2 divides m sub 3. So once again, d sub 2 divides any linear combination of these two integers. In particular, d sub 2 divides d. That is, d sub 2 divides d sub 1 times d over d sub 1, which is an integer, as d sub 1 divides d. Now, since the greatest common divisor of d sub 1 and d sub 2 is 1, that is, d sub 1 and d sub 2 are relatively prime, we have that d sub 2 divides d divided by d sub 1. So the product d sub 1 times d sub 2 divides d, and hence d sub 1 times d sub 2 is less than or equal to d. And so d is equal to d sub 1 times d sub 2. So now we can use the lemma to prove the following theorem. The direct product of integers modulo m sub I is cyclic if and only if the integers m sub I, for I in the range from 1 to n, are pairwise relatively prime. So proof. Suppose that the direct product is cyclic, then any subgroup of this cyclic group is cyclic. In particular, the subgroup, the integers modulo m sub I, cross the integers modulo m sub j, where I is less than or equal to 1, which is strictly less than j, which is less than or equal to n, is cyclic. And so the greatest common divisor of m sub I and m sub j is equal to 1, where once again I is less than or equal to 1, strictly less than j, which is less than or equal to n. That is, the integers are pairwise relatively prime. So conversely, Suppose the integers m sub I are pairwise relatively prime. Since the greatest common divisor of m1 and m2 is equal to 1, the direct product of the integers modulo m sub 1 with the integers modulo m sub 2 is cyclic. And so this product, the integers modulo m sub 1 times the integers modulo m sub 2, is isomorphic to the integers modulo m sub 1 times m sub 2. And once again, since the greatest common divisor of m sub 1 and m sub 2 is 1, the greatest common divisor of m sub 1, m sub 2, and m sub 3 is also 1. And so the greatest common divisor of the product m sub 1 times m sub 2 and m sub 3 is equal to the greatest common divisor of m sub 1 and m sub 3 times the greatest common divisor of m sub 2 and m sub 3, which is 1 times 1, which is 1. And hence the direct product of the integers modulo m sub 1 times m sub 2 times the integers modulo m sub 3 is cyclic. And so this product is isomorphic to the integers modulo the product m sub 1 times m sub 2 times m sub 3. That is, the product of the integers modulo m sub 1 times the integers modulo m sub 2 times the integers modulo m sub 3 is isomorphic to the integers modulo m sub 1 times m sub 2 times m sub 3. Now, since the greatest common divisor of the product m1 times m2 and m3 is equal to 1, we have that the greatest common divisor of the three integers, the product m1 times m2, m3, and m4 is 1. And so the greatest common divisor of the product m1 times m2 times m3 and m4 is equal to the greatest common divisor of the product m1 times m2 and m4 times the greatest common divisor of m3 and m4. Further, since the greatest common divisor of m1, m2, and m4 is equal to 1, we have that the greatest common divisor of the product m1 times m2 and m4 is equal to the greatest common divisor of m1 and m4 times the greatest common divisor of m2 and m4, which is 1 times 1, which is 1. And so the greatest common divisor of the product m1 times m2 times m3 and m4 is equal to 1 times 1, which is 1. And hence the direct product of the integers modulo m1 times m2 times m3 times the integers modulo m4 is cyclic. And so this product, the integers modulo m1 times m2 times m3 times integers modulo m4 is isomorphic to the integers modulo m1 times m2 times m3 times m4. That is, the product, the integers modulo m sub 1 times the integers modulo m sub 2 times the integers modulo m sub 3 times the integers modulo m sub 4 is isomorphic to the integers modulo m sub 1 times m sub 2 times m sub 3 times m sub 4. Now let k be a positive integer that is greater than 4 and less than n, and suppose that the product of the integers modulo m sub I is isomorphic to the integers modulo m sub 1 times m sub 2 and so on through m sub k. Then, since the integers modulo m sub 1 times m sub 2 through m sub k is isomorphic to the product of the integers modulo m sub 1 times m sub 2 through m sub k minus 1 times the integers modulo m sub k, we have that the greatest common divisor of the product m sub 1 times m sub 2 through m sub k minus 1 and m sub k is 1. And so the greatest common divisor of the product m sub 1 through m sub k minus 1, m sub k, and m sub k plus 1 is equal to 1. And hence the greatest common divisor of the product m sub 1 through m sub k and m sub k plus 1 is equal to the product of the greatest common divisor of the product m sub 1 through m sub k minus 1 and m sub k plus 1 times the greatest common divisor of m sub k and m sub k plus 1, where the greatest common divisor of the product m sub 1 through m sub k minus 1 and m sub k plus 1 is equal to the product, the greatest common divisor of m sub 1 and m sub k plus 1 times and so on through the greatest common divisor of m sub k minus 1 and m sub k plus 1, which is 1 times and so on through 1, which is 1. That is the greatest common divisor of the product m sub 1 through m sub k and m sub k plus 1 is equal to 1 times 1, which is 1. And so the product of the integers modulo m sub 1 through m sub k times the integers modulo m sub k plus 1 is cyclic. And hence this product is isomorphic to the integers modulo m sub 1 times, and so on through m sub k plus 1. That is, the product of the integers modulo m sub I is isomorphic to the integers modulo m sub 1 times m sub 2 and so on through m sub k plus 1. Correction. The product from I equals 1 to k plus 1 of the integers modulo m sub I is isomorphic to the integers modulo m sub 1 times m sub 2 through m sub k plus 1. That is, the case k implies the case k plus 1. Thus, by induction, we have that the product of the integers m sub I is isomorphic to the integers modulo m sub 1 times m sub 2 through m sub n. And hence this product, this direct product, is cyclic.